Welcome back, and thank you for joining me once again. Without much ado, let's get started. Question number 6. Some properties of diamond are shown. It is very hard. Every atom forms four bonds. It does not conduct electricity. Which properties are also shown by silicon 4 oxide? Okay, the first statement is very hard. That's very true because diamond is a very hard substance, and each carbon atom forms four covalent bonds in diamond and does not conduct electricity simply because all the electrons, the valence electrons in diamond were used in bond formation. And that's one of the major reasons why diamond wouldn't conduct electricity. And I think that answers the question on it does not conduct electricity. Then every atom form four bonds. Yes, because carbon or diamond is a tetravalent element, and that's why it forms four bonds. Okay, now let's compare that with silicon 4 oxide. Silicon 4 oxide also has a very strong covalent bonding between silicon and oxygen atoms, creating a giant lattice structure similar to diamond. Therefore, while selecting the correct answer for this question, we go with option C. Option C is correct. So, 1A is wrong, B is incorrect, but option C is correct. That is, it's very hard. It does not conduct electricity. Fine. Question 7. Which statement describes the attractive forces between molecules? Let's look at the first statement or the first option. They are strong covalent bonds with the covalent bond holding the molecules together. Okay, the option B says they are strong ionic bonds which hold molecules together. Option C, they are weak forces formed between covalently bonded molecules. Option D, they are weak forces which hold ions together in a lattice. All right. The statement that best describes intermolecular forces is they are weak forces formed between covalently bonded molecules. Therefore, if we look at option C, this is clearly stated in option C because covalent bonds hold atoms within a molecule together, but the forces between the molecules are typically weak. And that is what the option C is suggesting. Fine. Let's consider the eighth question. Which substance is described as a macromolecule? Macromolecule. The word macromolecule it means giant molecule. Giant molecule simply because these are made up of smaller molecules coming together in bonding to form a giant molecular structure. And this is observable in graphite. This is observable in graphite. Unlike in ammonia, where we have simple atoms coming together, nitrogen and hydrogen, and iron is an element. On the other hand, sodium chloride is a compound. It's a compound. So the correct answer for question number 8 is graphite. Okay, let's look at question number 9. The equation for the reaction of sodium with water is shown. That is represented by this chemical equation. Now the question is, what is the volume of hydrogen gas measured at RTP produced when 18 grams of sodium reacts with excess water? All right, from the equation of reaction, we could see that two molecules of sodium gave us one molecule of hydrogen gas, right? But one molecule of any gas at RTP is equal to 24.0 dmq, 24.0 dmq, right? Okay, now one molecule of sodium is actually 23 gram, per molecule, 23 gram per molecule for 1 molecule of sodium. But in this case, we have two molecules. That is 23 times 2. That's 46 gram of sodium in this reaction. Now, it's very clear that of sodium, 46 gram of sodium gave yield to 1 molecule of hydrogen gas, 1 molecule of hydrogen gas, right? Okay, now 18.4 gram of sodium, 18.4, 18.4 gram of sodium will produce how many mole of hydrogen gas? Hydrogen gas. I hope you are getting what I'm trying to explain here. 46 gram of sodium give yield to 1 molecule of hydrogen gas. How about 18.4 gram of sodium? How many molecule of hydrogen gas will that produce? Okay, if we cross multiply and make S the subject of the formula, we will definitely get 40, okay, 18.4 gram. That is 18.4 gram. That's the mass of sodium divided by 46 gram. 46 gram. And that gives us what? 0.4 mole of hydrogen gas. 0.4 mole of hydrogen gas. Okay, now that we have 0.4 mole of hydrogen gas produced as a result of matching the mass of sodium with the molecule of hydrogen gas being produced. It is time for us to appropriate the correct formula for getting exactly the volume of hydrogen gas, and that's we could do by converting 0.4 mole of hydrogen gas to the volume. Let's use the formula mole amount in mole is equal to the volume divided by the volume as RTP volume. That's the RTP volume. Okay, now we have 0.4 mole of hydrogen gas being produced. Then the volume we are looking for the volume produced at 0.4 mole, right? Then our RTP value is 24.0, 24.0. So when we cross multiply multiply 24.0 dmq by 0.4, we definitely get 9.6 dmq as the new volume of hydrogen gas being produced as a result of using 18.4 gram of sodium. Right? Let's look at question number 10. Iron can be electroplated with zinc to make it resistant to corrosion. Which rule about electroplating iron with zinc is correct? Okay, and I would like to mention that this is purely electroplating. Electroplating is a situation whereby it's a process of coating a metal with another metal just to improve the appearance and to improve the quality. That is exactly what we described previously when we talk about alloy. Mixing of metal with another metal is purely a mixture, but in this case we are coating a metal on another metal using electricity, and that is why it is electroplating. Okay, now we want to coat iron with zinc using electricity, and the modus operandi for that is making the cathode our iron. That's the substance to be electroplated. Iron is going to be our cathode. Okay, the reason why we are making iron the cathode is because metals are deposited on the cathode. Why? Because At the cathode, we have a reduction reaction taking place there where there is a gain of electron. Reduction reaction, there is a gain of electron in reduction reaction, and once that happens, there is going to be a coating of a metal on the cathode. The anode is our zinc. That's the zinc is the anode. The anode is the zinc, and at the anode, oxidation reaction takes place at the anode, and the oxidation reaction involves the loss of electron. There is going to be a loss of electron because zinc metal is going to lose two electrons, and when that happens, zinc becomes iron, and this iron is deposited into the solution of the electrolyte. And right in the electrolyte, the movement of these ions towards iron takes place. And when the ion comes to the cathode, where reduction process takes place, we have zinc ion, which is the ion to be coated, gain electron, and when that happens, we have a deposition of zinc atom on the ion on the cathode. So this is the first equation is the anodic equation, while the second equation is the cathodic equation. The first equation is oxidation reaction, while the second equation is a reduction reaction. So zinc 2 ion is going to lose, I mean, it's going to gain two electrons, and when it gains two electrons, it becomes deposited as zinc atom, and that will be coated all over the surface of our iron, and that is what electroplating is all about. So this process, now to answer this question quickly, we look at which of the metal is made the anode and which of the metal is made the cathode, and the electrolyte can be any of the zinc salts. Okay, now, and this qualifies for that. The zinc nitrate in B and D qualifies for that. All right, let's look at option A. Excuse me. Option A says iron is going to be the anode, while zinc will be the cathode. Obviously, this is incorrect. Okay, now let's look at option B says iron is going to be the anode, while zinc is going to be the cathode. All right, this is equally very wrong. If you look at option C, which says the anode is our zinc, that's true. The anode is the zinc, but and the iron is the cathode. That seems true as well. Well, if you look at the electrolyte here, there's a problem. Iron nitrate is not going to be used. Okay, now the last option says zinc is our anode. That's fine. And the cathode is iron. Then the solution of the electrolyte we are using is zinc nitrate. Okay, that is perfect, and that is the correct answer for that question. Right, the 11th question says chlorine reacts with ethane to produce chloroethane and hydrogen chloride. Right, the reaction is exothermic. When a reaction is exothermic, it means it is a reaction that is releasing heat to the environment. See, in exothermic reaction, the containing vessel is usually very hot, and we see the change in enthalpy. The change in enthalpy of every exothermic reaction is depicted with a negative value, the negative value of the per mole, energy per mole. Now, the bond energies are already specified in this table. The bond between chlorine, the carbon to chlorine is 340, carbon to carbon 350, carbon to hydrogen is 410, and chlorine to chlorine 240, hydrogen to chlorine 430. Okay, well, I want you to consider that for every exothermic reaction, the bond forming energy is usually greater than the bond breaking energy. On the contrary, for endothermic reaction, the bond breaking energy is usually greater than the bond forming energies. Okay, now if you consider this equation, the energy in minus the energy out will give us precisely what our answer is in these options. Okay, now if we look at the bond between carbon to hydrogen here, carbon to hydrogen here as specified here, this is 410. Carbon to hydrogen 410, another carbon to hydrogen 410, another carbon to hydrogen 410. Now, this equally carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. If we multiply the number we have here, 4 and 10, by the number of carbon to hydrogen bonds here, and that will help us to calculate precisely the total energy in 18, the total energy in 18. Okay, we do the same thing with chlorine atoms. Of course, chlorine to chlorine atom here, we have 240. That's the energy here. So in a nutshell, before we go on for this, let's quickly write the 240. That is the energy here, plus the energy in ethane can be calculated. Therefore, by simple calculations, carbon to hydrogen bond here in how many places? Carbon to hydrogen 1, 2, 3, 4, 5, 6. Okay, so we have 6 carbon to hydrogen bonds, and the value of carbon to hydrogen bond from the table is 410, 400, and 410 for carbon to hydrogen bond, equally carbon to hydrogen, carbon to carbon has a value of 350, and that is what we have here between this first carbon and the second carbon. We had this, that's for 18, strictly for 18. Then we have an outstanding 240 for the two chlorine atoms. The summation of these value will give us the energy in. Okay, and then let's do that by cap. I have a total of 3,050 for the energy in. Let's go ahead and calculate the energy out on the product side simply by adding the carbon to hydrogen bond here. In how many places now? Let's find out. 1, 2, 3, 4, 5. We have carbon to hydrogen bonds in 5 places. That is multiplying carbon to hydrogen bond. That's multiplying 4 and 10 by 5. And equally, don't forget that carbon to carbon bond is specifically 350. You have that too. And the carbon to chlorine atom. So this bond equally, which is 340, add all these together with hydrogen to chlorine atom, which is 430. So adding all this together gave me a value of 3,170. Now, don't forget that the energy in and this is the energy out. Okay, now when you take away the energy out from the energy in, you tend to get a value which is negative, minus 120 kilojoule per molecule, and that is the value we have here as our calculation depicting the exothermic reaction as said earlier in that equation. Okay, thank you for today. Thank you for joining me, and please watch out for the next section. We continue from question number 12 in the next video. Please subscribe, like, and share. Okay, to remain again. Bye for now.